morning, dear students. Today we are going to learn about ATP synthase. What is ATP synthase? It is a protein. It is an enzyme. It catalyzes the formation of ATP, that is adenosine triphosphate. From where? From ADP, adenosine diphosphate. Okay, that is a function. In another way also we can explain its function in this form. It combines the oxidation reaction of NADH to the phosphorylation of ATP. So that's what happening. In our body, for all function, we need energy, and our energy currency is ATP, that we all know. So it's very ultimate to synthesize ATP in abundant level. And for its phosphorylation, the cell requires energy. That energy is obtaining because of the oxidation of NADH. And from where this NADH is coming? It is producing as part of several metabolic pathway. Metabolysis of carbohydrates, so many things. It is forming in so many different metabolic pathway. This NADH is forming. It is energy rich. Its oxidation releases energy, and that energy is used up to phosphorylate and synthesize ATP. Okay, so in simple form, we can tell that ATP synthase is the enzyme responsible to synthesize ATP. Let's see some other synonyms of this ATP synthase enzyme. They're called as elementary particles, they're called as oxysomes, F1, F0, ATP, ATPase. So, whenever you come across any of these terms, you need to understand that all these things are ATP synthase itself. And don't get confused of seeing this type of questions in your question paper. Okay. Oh, sorry. Okay. Uh, where we can locate this ATP synthase? It spans the inner mitochondrial membrane. It spans the first. I think that you know the structure of mitochondria. It has an outer membrane and a folded inner membrane. And this ATP synthase is present. It spans the inner membrane. In this way, it presents this ATP synthase. It spans the inner mitochondrial membrane. What are its subunits? Main subunits are this one together is the F0, and this one together is called the F1. So mainly F1 and F0 is the main subunit, and there is a stalk also we can see here. And this F0 portion, it is the transmembrane. Transmembrane means it is the part of this enzyme that is spanning the inner mitochondrial membrane. And it is composed of 10 to 12 subunits. 10 to 12 subunits in the form of a ring that forms that F0 part. And it forms a channel. Here a channel is there, a pathway is there, and through that pathway protons can move. And that F1 portion and that stalk, it consists of 5 different kinds of protein. Later in the coming slide, I will explain more about these subunits. Now you just heard about the names. They are alpha, beta, delta, gamma, epsilon. They are in the means order. Means what about its number? Alpha and beta, they are 3 each, and delta, gamma, epsilon are 1 each only. And yeah, this F1 is the main site for ATP synthesis. Yeah. So ATP synthase function, ATP synthesis, other names where we can locate that ATP synthase and subunits, mainly F0, F1. And each subunit is composed of what all things. And who demonstrated the action of this enzyme? Two scientists. One American scientist called the Paul Boyer and a British scientist John Walker. They demonstrate the action of this enzyme. So we are going to see the functioning. I already told you that NADH is an energy-rich molecule formed during the metabolic pathway, metabolism of several substances like carbohydrate, protein, like that. And from the NADH, electrons are moving through different enzymes that present in the inner mitochondrial membrane. And that movement, it is an exergonic process. Exergonic process means it is an energy releasing process. And because of that exergonic process, I told you that energy is releasing, and that released energy is used up to create a proton gradient across the inner mitochondrial membrane. And that proton gradient is again tapped or used to synthesize the ATP. And that process is an endergonic process, energy recurring process. So that's what I'm going to show you once more. This is the inner mitochondrial membrane. Mitochondrial membrane. And this is the inner mitochondrial space. And outer to that, the outer membrane is present. And this is the matrix inside the mitochondria. And we can see an array of different complexes that are part of the electron transport chain that present in the inner mitochondrial membrane. So let's see here the NADH is the forming here, and it is an energy rich molecule, and from it the electron is moving through all these subunits. As it moves, it releases enormous amount of energy, and using this energy, proton from the matrix is moving out using that energy. And as this protons moves a lot of time across this inner mitochondrial membrane, that can create a high concentration of protons here in the inner mitochondrial space. So much protons will reach here. And after that, the concentration of protons in this space become high, and it tried to move back to the matrix in the direction of concentration gradient. Oh, sorry, concentration gradient. That's what. And that movement of the proton takes place through the central channel that present inside the F0 subunit of the ATP synthase. As it moves down, it gives energy, it releases energy, and using this energy, this portion, this stalk, it rotates, and because of the rotation, the ATP synthesis, phosphorylation of ADP happens here in this portion, that is the F1 portion, and ATP is synthesizing here. So that is the method, that is the process that is happening. Okay, is it clear? So once more I am going to explain everything. This is the inner mitochondrial membrane. Here we can see the ATP synthase. And I already told you, explained to you different subunits of this ATP synthase. 5 different polypeptides we can see. 3 alpha, we can see 3 alpha is arranged in the form of ring around here. Alternate with the 3 beta. 3 beta. So 3 alpha and 3 beta alternatively arranged in the form of a hexamer here. Okay, and along with that we can see that stalk, this gamma stalk. Associated with that, another subunit present, epsilon, is there, and this beta subunit in this hexamer is involved directly in the catalysis of ADP to ATP conversion. So this is involved in that synthesis process or catalysis process. And each beta, here we can see 3 beta, 1, 2, 3. Each beta is interacting with this stalk gamma in 3 different position, three different interfaces. So they are communicating in 3 different interfaces, each beta. So that's also an interesting thing. And this F0 portion, this F0 portion is a hydrophobic portion, and that F1 portion, it is the hydrophilic portion. That also we need to understand. And I already told you here a proton channel is there, and you through this channel the protons in the direction of concentration gradient is moving to the matrix. And this ring is formed of 10 to 40 subunits. 10 to 40 subunits. Which one? This ring. And it is called C subunits. And we can see a single A subunit outer to this ring, C subunit ring. And also this F0 binds or connected with this F1 by 2 way. Which are those 2 way? 2 way, one way is through the stalk and the other way is through the 2B subunit and one delta subunit and this outer A subunit. So by this 2 way, the F1, this is the F1 and F0 is connected with each other. So these are some points we need to understand. And in this enzyme, it is a moving part. Moving part is this ring. Ring is the moving part, and also that stalk. Stalk also is the moving part, and the remaining portions are stationary. And the process of synthesis of ATP, it happens in these 3 steps, like binding of one ADP and one inorganic phosphate, then ATP synthesis and ATP release. These are the 3 steps. So then we need to understand one more thing. These 3 beta subunit, they exist in 3 different conformation as it interacts with the 3 phases of this gamma stalk. So depends upon its interactive phase with the gamma subunit. 3 beta subunit exists in 3 conformation. Which are those 3 conformations? They are L conformation, T conformation and O conformation. And what is the state in each conformation? That also we need to understand. In L conformation, it can bind one ADP and one molecule of inorganic phosphate. In tight conformation, it can combine this ADP and inorganic phosphate to form one ATP, but it cannot release that to form the ATP. And in O conformation, it become able to release that formed ATP. That means each beta subunit need to change from one conformation to another to finally release the formed ATP. How it is happening, that shift from one conformation to another and another conformation, that is happening because of the rotation of this gamma stalk. And that rotation, how it happens, I already explained to you. As the proton gush through that channel, that release energy, and using that energy, that stalk is rotating, and because of that rotation, each beta subunit change its conformation and finally results in the release of the ATP. So that is the process. That's what I am going to show you once more. This is a cross-sectional type view. Here in the center, you can see that gamma subunit, and this one is beta, one beta, this is another beta, this is another beta. And as I already told you, these three are in three different conformation at present. And what is its present conformation? Suppose this is in T conformation. This one is in T conformation, and this one in L conformation, this one in O conformation. Suppose you think like that. And this gamma is going to rotate in anti-clockwise direction for 120 degree. Let's think like that. As it rotates, there will happen a shift for each conformation. Conformation shift always happen from T to O. In that way, that conformation change is happening. T to O likewise. And then O become L. So this is the order of that change in conformation. So as it finish one round of anti-clockwise rotation of about 120 degree, then this T will change its conformation to O. And we need to understand that in T conformation, already one ATP is formed here. T conformation. As it shift to O, then that subunit become able to release that ATP. Now it become O conformation only because of this rotation. And this L, we know that from the L again need to move back to tight conformation. Tight. Then what happens here? At L conformation, we know that it will hold one ADP and inorganic phosphate. As it changed to tight conformation, it form one ATP there, but it cannot release. And here what happens, as that because of that one rotation, it release that formed ATP. So these are the change happen. And again as it rotate, what will happen? From here, that formed ATP released, and from here what will happen? That tight again become O, and here what will happen? This O will become in L conformation again. So this is repeating and repeating. Only thing is that because of the rotation of that stalk, this beta subunit change its conformation. As it changes its conformation, ATP is synthesizing and releasing. So that is a function of ATP synthase. Okay, I hope that is very, very clear to you. With this, I am going to wind up today's section. Thank you.
I'm an icon, man. Ain't my girl about a 10. I should fuck her in the Benz.